All right, and welcome to our next unit in Chem Honors, where we're going to be looking at acids and bases. Now, we have two handouts for today's lesson, and one of them is a demo. We'll get to that in a moment. But for right now, before we get to the demo, I want to make a couple of definitions because the way the demo usually works, we'll have done part of the demo, and then we're going to go through and fill in some other parts of the demo that are already filled in, but we're going to want to be able to know what we're talking about. So in the demo, we're going to be looking for the differences between compounds which are non-electrolytes. So we talked about electrolytes before when we talked about ionic compounds. And a non-electrolyte is just any substance that does not conduct electricity in any form, either dissolved in water when it's aqueous or when melted when you heat it up. Now, we've seen ionic compounds as electrolytes, but they're not the only ones. An electrolyte is going to be any substance that conducts electricity in some form, whether it's aqueous, dissolved in water, or whether it's melted. And there's three classes of compounds that can be electrolytes. Acids are one, and those are going to be compounds with a pH below 7. Bases with a pH greater than 7. And hopefully you've seen these definitions before. We'll get back to those a little bit later on in this unit. And salts, which are basically just ionic compounds that are neither acids nor bases. In other words, they don't have any hydrogen ion in them, as an acid would, or hydroxide as a base would. And we're going to see how those work. And we're also going to be looking for the difference between strong electrolytes versus weak electrolytes. So with that in mind, let's go take a look at this conductivity demo chart and write-up. So in here, we're going to see a bunch of different compounds. Now, typically what would have happened is we would have done this in one class period, and then we'd be coming back in the next class period to look at it and to figure out what sense the data makes. So let's go through the data, and let's start assigning different compounds to different kinds of what their bonding is, and also what whether acids or bases or not, and whether they're electrolytes or non-electrolytes. So we started off with distilled water, number one. And distilled water, because there were no ions, it's distilled or deionized. No ions means, no conductivity means there's no ions. And it turned out that distilled water is neutral, and so we call that a non-electrolyte. Doesn't conduct electricity. Sodium chloride. Sodium chloride is an ionic compound. So remember that ionic compound here. As a solid, there's no free ions because it's the solid state, so no conducting electricity, and no pH as well because there's no water. You need water to have pH. So without water, you can't have a pH. Sodium chloride, when you dissolve it, lots of ions and strong conductivity. Still neutral, pH is 7, and we call that a salt. That has an ion, it has a cation and an anion, and there's no H plus or OH minus in it. Now be careful with this next one. It looks like there might be OH minus in there, but this is not ionic because there's no metals. Right? There's no metal, so we can't have an ionic compound. And pure ethanol has no ability to conduct electricity. There's no ions. And ethanol, when you dissolve it in water, has no conductivity as well. It is neutral because we're putting in neutral water. It's a polar covalent compound, but because of no conductivity, it's a non-electrolyte. 6 and 7 are both non-polar covalent molecules. They don't dissolve in water, and they don't conduct electricity, and so those are non-electrolytes as well. These next three are sulfuric acid, nitric acid, and hydrochloric acid. You may remember those from chapter 8 when we did our naming. So we know that they're acids. We confirm that they're acids because they have a pH of 1, so that makes them an acid. It also turns out that these have a lot of high conductivity. So with our conductivity light bulb, the light bulb is going to glow very strongly, which means they all have lots of ions. So the number of mobile ions is going to be lots of mobile ions. So we can consider these guys to be strong electrolytes. Acetic acid. In pure acetic acid, I'm not sure how we have a pH because there's really no water in there. No conductivity, there's no mobile ions because it's pure. But when we dissolve it in water, so this is in water, when we dissolve it, we get some dim conductivity. So this becomes a weak electrolyte. And that's because we have some ions. And a pH of 3, somehow, you know what, I don't know how that happened. There can't be a pH of 5 in CCl4 because there's no water. But in tetrachloromethane or carbon tetrachloride, there's no conductivity because we have a polar covalent compound dissolved in a covalent compound. There's not going to be any conductivity. And sorry about that jumping of the PC there. It is an acid, however. It's an acid, and we know it's an acid because it's got that H at the end. The COOH makes it an acid. 14 through 17, these are bases. 2 of the bases conduct electricity a lot, so they're strong electrolytes. They have a very high pH, meaning they're basic. They are ionic, but they're not salts. There's a difference between an ionic compound and a salt. These are bases. Calcium hydroxide, barium hydroxide, these are weak electrolytes. And so is ammonia, a weak electrolyte. They all have dim conductivity, dim light bulb with some ions, and a lower pH, so weaker bases, but they're all bases as well. Now look at this. This is where things are going to get interesting. The first 2 are ionic, but the ammonia is polar covalent, and how that becomes a base is going to be an interesting story we'll talk about. We'll see it a little bit. Now, calcium nitrate and barium chloride, these are going to be like sodium chloride. They're both salts. They're both ionic. They both dissolve and give us strong electrolytes and lots of electricity, and they're both neutral. So we get some correlation there. Glucose, sugar, is a non-electrolyte because there are no ions. So there are no ions, and we'll see how this works when we show you the equation for dissolving this in water. Now, in water, it does give us a pH of 6. I'm not sure why that happened. It's close enough to 7. We can say it's pretty neutral, and it is polar covalent. And that's going to give us some idea of properties we expect from it. Finally, sodium acetate. Sodium acetate is ionic. We can split the sodium acetate at the sodium and the acetate. As the solid, again, solid, there's no ions free. And as the liquid, then we can, aqueous, we can dissolve it. We get lots of ions. And so it's a strong electrolyte, pH of 8. It is slightly basic. And finally, when we melt it, this has an off melting point that I could melt it, and I would have if we were doing the demo. And when I melt it, we see high conductivity, strong electrolyte, lots of ions. Now, let's take a look at some of the structures of these covalent molecules, because this is where things get interesting. 4 and 5 is ethanol, and ethanol is polar covalent, but it doesn't conduct electricity because its OH bond is less polar and stronger than 8, 9, and, 12, really, where we had the acetic acid conducting electricity. So what's going on there is that this OH bond stays intact. But in 8, 9, and 12, we're going to see that that OH bond comes apart. The OH bond can come apart. And the reason for that coming apart has to do with the fact that the oxygens on the other side are pulling electrons. They're pulling electrons away. So the electrons are getting pulled away, making this H plus more polar. So making that H plus more polar. and it's going to weaken that OH bond and make it so that H can be nabbed by water, as we'll see. The same thing happens in number 10, where the chlorine is pulling away enough of the electrons from the H plus that we can break that bond in water. So this is how we can make acids from polar covalent molecules. 6 and 7 are both nonpolar covalent. There's no ions to worry about. There's nothing to dissociate, no metal there, no polar bond at all. And so there's nothing to dissociate. In number 18, there is a polar bond, but the polar bond is not the one that's going to break. And we're going to see something interesting with number 18. Number 21 and 22, the glucose has the same thing as the ethanol in number 4 and 5. We got those COH bonds. There's one COC bond, but those COH bonds are all less polar and stronger than 8, 9. I'm going to write 12 here. Let's cross off 11 there and put 12 because it's really 12. That was the one that conduct electricity. So keep those in mind. I'll refer back to those as we go to finish up over here. Now, finish up. We've got a lot of stuff to do here. So let's talk about what's going on with the dissolving and melting as we look at these compounds. So the ethanol, when you dissolve it in water, so let's put H2O over the arrow to say that we are dissolving this in water. We just take that ethanol and through hydrogen bonding, the CH3, CH2OH becomes aqueous. And that's due to hydrogen bonding. Hydrogen bonding, but there's no ions. It's not splitting apart. It doesn't split at that OH because that OH split at the C because we have a COH. That CO bond is strong, and so it's not going to break apart, not like an ionic bond will. All right, so we're not going to break that apart. Glucose, we also have lots of CO bonds, OH bonds, and so when we put that in water, it's going to dissolve, C6H12O6, aqueous. Again, we get hydrogen bonding, but no ions. That doesn't look like a no ions. When we melt it, so suppose we took the glucose and we melted it, all we do is breaking those hydrogen bonds, but no ions. Finally, with the nonpolars, if I try to put the nonpolar materials into water, no reaction, nothing happens. There's no ions formed. So no electrolytes, no conducting electricity for these guys. Let's review, take a look at what's going on, and actually a little something new with salts going on here. So sodium chloride, if I take sodium chloride and I put it in water, I'm going to put the water there. Again, it's not really part of the reaction. I'm going to make sodium ions, and those are going to be aqueous, and chloride ions, and those are also going to be aqueous. And we get 100% dissociation. So 100% dissociation gives us lots of ions, and makes this into a strong electrolyte. Oh, by the way, all these guys as solids, the ions are locked. Locked in the lattice, and so no conductivity. Calcium nitrate, do the same thing. We're going to split anion from cation when we put it in water, make calcium 2 plus, aqueous, and now watch your stoichiometry. We've got 2 hydroxides, again 100% dissociation. So we have a strong electrolyte. Sodium acetate will do the same thing. So when we dissolve it, we're going to make H2O. It's going to take us into sodium ions. And the acetate ion, CH3COO minus. By the way, acetate can also be written C2H3O2 minus, depending on how you want to present it. And that's aqueous. AC, not AQ, not AG. And again, lots of ions. Now, calcium carbonate is an interesting thing. We saw that calcium carbonate and barium carbonate. We saw one of these guys was actually a weak electrolyte. So this is weak. Why is this a weak electrolyte? You notice I've got an equilibrium arrow there. When we put calcium carbonate into water, we do make calcium ions and the carbonate ions. But this is something we actually skipped over in equilibrium in the interest of time. This kind of a salt doesn't dissociate 100%. This has less than 100% dissociation, which again makes it a weak electrolyte. Because it has less than 100% dissociation, we actually can write an equilibrium constant for us. So this is an equilibrium. And the equilibrium constant, because of the low solubility, has a special name. We give it a K for equilibrium, but SP for the solubility product. And you don't need to worry much about that. But just the fact that some salts that we originally said were not soluble, like if you look at your solubility rules, calcium carbonate is going to come up as not soluble. It actually has a small but non-zero dissociation, and that would have been given by a KSP. Calcium carbonate, when you melt it, so if this was one that we melted, then that would make the calcium 2 plus ions as a liquid and the carbonate ions as a liquid. Now we would get lots of ions and conductivity. Okay, so those are ionic compounds known as salts. Now let's turn our attention on the next page to acids. So in acids, we're going to find that we have a polar covalent molecule. And this polar covalent molecule with an H plus that's easily removed. And that's easily removed because the bond that it's on, the HX bond, is not just polar, very polar. And I showed you the structures before and how having the oxygen, those electronegative oxygens, pulling electrons away from the hydrogen ion is going to make it more polar, or in the case of the chlorine, it's going to make a weaker bond, and that's a little bit beyond what I want to go into. Now, let's put some delta plus, delta minus on here, just to remind ourselves what we've got here. Delta plus, delta minus for the HCl. That's that polar bond. And let's put some water here. And we're going to put water in here. The water could actually be part of the reactants. And in the next couple of days, we're actually going to make it part of the reactants. For now, it's there, but it is actually serving a purpose. Now, remember, water has these lone pairs on the oxygen. Those lone pairs are going to be able to take that hydrogen, and it takes that hydrogen and pulls it off onto the oxygen on the water. And we're going to make something called H3O+. H3O+ is hydronium ion. And it's really what's made when you take an H plus and an H2O together. Often we just think of it as H plus for simplicity, but it is H3O+, and that's aqueous. And we also have some chloride in there that's also aqueous. Now, this is a strong electrolyte because it's a strong acid. Strong acid, 100% dissociation. And so when we had the light bulb in here, it glowed very, very brightly. Lots of ions. Sulfuric acid does the same thing. Excuse me, I've got to blow my nose. So sulfuric acid, let me write the structure for sulfuric acid to remind you rather than having to go back. So sulfuric acid has that sulfur surrounded by 4 tetrahedral oxygen atoms, and 2 of those oxygen atoms actually have hydrogen atoms bonded to them. So when we write H2SO4, the H's are not on the sulfur, but they're on the oxygens. If we put in our partial charges, partial negative on the oxygens, partial positive on the sulfur, negative, negative, and partial positives on that hydrogen. Now, when we write water up here, we're going to have the same thing happen. We're going to have the water molecule is going to take one of those hydrogen atoms. It's going to split the OH bond. It's going to take one of those hydrogen atoms off of the OH bond because this is a very polar bond. And we're going to make the H3O plus. And it's going to also make hydrogen sulfate, HSO4 minus. That's also aqueous. And this is a strong acid and a strong electrolyte. So these are both strong electrolytes. They dissociate 100%, which is not what happens with acetic acid. Now here I've written the H plus in front. So here's my H that comes off. Now you notice there are 3 other H's on here. Those 3 other H's are non-acidic. They're not acidic. And because they're on a carbon, the carbon-hydrogen bond is nonpolar. And so those 3 hydrogen atoms are never going to be considered acids. They're never going to be involved. Write the acidic hydrogen separately. Whenever we have 2 different kinds of hydrogens, please write that acidic hydrogen separately. Now you'll notice I also have here an equilibrium arrow because this is an equilibrium. So let's write the ions first, and we'll talk about that equilibrium. So the ions are going to be, again, if we have water, we're going to do the same thing. We have those lone pairs, and the water is going to take off that hydrogen ion and make H3O plus, and aqueous, not an Ag, but AQ, sorry about that, and acetate CH3COO minus, the acetate ion. Now, this is a weak acid. Remember, it had low conductivity, so it was a weak electrolyte. It's also a weak acid. Electrolyte. And it turns out that it is only about 0.1% dissociated. So this is one of those important weak equilibria that I was talking about. This has an equilibrium. And we'll talk more about these later on. Because it's an acid, it has a special subscript. Instead of KEQ, it's a Ka for acids. And the Ka is much less than 1 because this is a reactant-favored reaction. And that makes important properties that we'll deal with some of those later on. All right, so this is an equilibrium, and we will deal with that in, 2 lessons. I think in 2 lessons we're going to start to deal with that as the exactly what that means. Now, the common theme that we've been seeing here is not only are they electrolytes, either weak or strong electrolytes, but also notice what's happening. We are taking that water and we're taking the H plus off of the acid. And so that gives us our first definition for what an acid is. So we're going to take a look at two models for acids and bases. And the Arrhenius definition, the Arrhenius definition is going to be our first definition. In the Arrhenius model, any acid is a substance that produces that produces H plus, thinking H3O plus, in water. All right, so anytime you have H plus or H3O plus in water from the substance, that's an Arrhenius acid. And that H3O plus is what gives us pH. And we'll talk about that next week. So those are acids. Now, the last kind of compound we have to talk about is a base. And in a base, what we're going to notice is that bases generally have hydroxide. And they're this ionic compound that has hydroxide, but because they have hydroxide, they're not considered salts. As before, we're going to put some water there to dissolve it. And when we dissolve it, they're going to split apart into the sodium ions and the hydroxide ions. And because this is a strong base and a strong electrolyte, so remember this glowed, if you look back on the other page, this glowed strongly, strong electrolyte. This is 100% dissociation. Every NaOH dissociates, and that gives us lots of ions. By the way, there is a difference between dissolving and dissociating, like the non-electrolytes showed you. For calcium hydroxide, as before, we're going to split this apart. Just like with the calcium nitrate before, we've got to watch our stoichiometry. Calcium 2 plus and 2 hydroxides. And again, strong, 100% dissociation. So a strong electrolyte. And then we get to this oddity, this ammonia. Now remember, ammonia had a dim conductivity, so this was a weak electrolyte. Don't jump ahead, because trying to figure out what's going on is a little tricky. To help us out, let's draw the Lewis structure for ammonia. Ammonia has, and I'm actually drawing the Vesper structure, the trigonal plane, a trigonal pyramid. And we have our delta plus, delta minus, delta plus on the hydrogens. And we have that equilibrium. We have that equilibrium again. Let me write out to the right here, just to get it down on paper here, that this is also an equilibrium, but because it's a base, we're going to have a KB rather than a Ka or just a regular KEQ. Does the same thing. It's just indicating that this is for a weak base. Now, when we put water here, let's see what happens. Actually, let's take the water and write out the Lewis structure for the water, because I want you to see how this is working. So again, delta plus, the delta minus on the oxygen, delta plus is on the hydrogens. And I forgot to draw in the lone pairs. Let's put those lone pairs on the oxygen. Now, what's going on here is that the water is the one that has the weaker bond with the hydrogen. So the NH bond is not as polar as the OH bond. And so what's going to happen is the OH is going to break apart. The OH bond is going to break apart, and we're going to make ammonium. So we've added the hydrogen to the ammonium, and that's aqueous. And now look at what we've got left behind. We've got hydroxide being left behind. And just like the pH was given by the H plus from the acids, it's the hydroxide that gives pH. The hydroxide that gives the pH. And we'll see how that works when we talk about pH later on. But for now, just realize that hydroxide is what's giving us the pH. This is a weak base. Like acetic acid, the dissociation is about 0.1% dissociation. So much, much less than 100%. And few ions. So, as I said, a weak electrolyte. So let's finish this up by writing our definition for an Arrhenius base. Now, we saw above that an Arrhenius acid is something that gave H plus in water. And so an Arrhenius base, you might reason, is going to be any substance that produces hydroxide, OH minus, in water. Now, there is another definition of acids and bases that I kind of hinted at in here, and you'll see more about that in the next lesson. But for now, this is quite enough, and hopefully you will have a little bit more understanding once you get through the homework. All right, I will see you in class next time. Take care.